Good.
Okay, so then we can just start the seminar. So thank you for accepting our invitation. So today we are glad to have so Jose Miguel No. He graduated from Autonoma University of Madrid, right? And he had postdoc experience at King's College and Sussex University, and now he's a researcher at the Institute of Theoretical Physics at Autonomous University of Madrid. So his talk today is extended scalar sectors and baryogenesis. So thank you.
Thank you very much for the kind invitation. It's an early pleasure to be here. And yes, as Ariel, as Ariel just said, I will be telling you today about non-minimal Higgs sectors and their impact on baryogenesis. Not quite what you are used to say. And this is based on two words that already came out in the last year and a half, plus another one that is ongoing. So that you can see here. So let me start with my motivation, which is, as the title suggested, the origin of the matter-antimatter asymmetry, which is trying to explain this number here. Do you see my cursor?
Yes.
Okay. So trying to explain the baryon to entropy ratio measured, for example, by the Planck collaboration. And in order to dynamically generate a baryon asymmetry, we need to fulfill the three so-called SAR of conditions: baryon number violation, C and CP violation, and departure from thermal equilibrium. And in the standard model, it seemed, if you would look at it from far away, you could say that these conditions would be satisfied, which triggered a lot of attention and a lot of research in the late 80s and early 90s of the last century. In particular, baryon number violation is present in the standard model via non-perturbative processes called the Sphaleron processes, which are a byproduct of the non-trivial structure of non-abelian gauge fields, of the non-trivial structure of the vacuum of non-abelian gauge fields. However, the second ingredient, CP violation, despite being present in the standard model by the fermion family mixing, is not there in a sufficient amount. And in particular, one can do a naive quick estimate of what would be the amount of CP violation that one would have at electroweak temperatures in the early universe, and this is extremely small. This is of order of 10 to the minus 20 as a ratio of dimensionful quantities. And this is roughly 10 orders of magnitude smaller than what you would at least need in order to explain the baryon to entropy ratio. Finally, the departure from thermal equilibrium is also not really there. It was thought that the electroweak phase transition, the breaking of the electroweak symmetry in the early universe, would provide such departure from thermal equilibrium. But in the standard model, it turns out to be a very smooth process. It's something which is not out of equilibrium at all. And thus, you don't get that in the standard model. However, the fact that these two ingredients seemed to be present, although not in a sufficient amount in the standard model, in nature, somehow tells us that electroweak baryogenesis is indeed possible if new physics beyond the standard model is not extremely heavy, so it's around electroweak scales, or maybe a bit higher, but not a lot higher. So let me call that light. But by light, I mean non-decoupled from the electroweak scale. And it also needs to be sizably coupled to the Higgs in order to influence the nature of the electric phase transition, in order to provide some departure from thermal equilibrium. Plus, of course, there is the extra need of CPU evaluation beyond the standard model. Now, most studies of electronic baryogenesis do focus on the departure from thermal equilibrium part. They study the modifications in the electric phase transition when you add new particles, etc., etc. Not all of them, but most of them. In this talk, I will try to concentrate on addressing more the CPU evaluating part rather than the other one. In the end, the two will be combined, but my focus is mostly on the CPU evaluation, and we will see why in a second. But before we jump into the talk, let me continue the introduction with a brief recap of what is usually discussed when one talks about electronic baryogenesis, which is the electric phase transition bit. Okay? So the electric phase transition is the breaking of the electric symmetry in the early universe. And in order to be able to describe this, I, of course, need to be able to describe the evolution of the Higgs in the early universe, the evolution of the vacuum of my theory in the early universe. And the tool that I have at my disposal, or that we have at our disposal to do this, is the so-called finite temperature effective potential, which is the scalar potential of the system of the theory one is working with, not only at tree level, but also including zero temperature radiative corrections, zero temperature loop corrections, and also thermal effects. Now, one can compute this finite temperature effective potential in a perturbative way, say in a loop expansion, for example. And the nature of the electric phase transition in this perturbative manner can be described via two different, say, qualitative setups. So if the Higgs develops a vacuum expectation value different from zero, away from the origin, at some point, and this development is somehow a continuous process, so as the temperature drops in the early universe because the universe is expanding, one goes from a situation where at very high temperatures the symmetry is restored, and below some critical temperature this vacuum develops, but it develops in a tiny manner, and it becomes larger and larger as the temperature drops. This is a continuous development of the web. This is a continuous process, and this is, from the point of view of thermodynamics, a second order transition, because the order parameter of the transition, which is the Higgs web, changes continuously. Now, alternatively, if the scalar potential develops a new vacuum away from the origin, but this is separated by the symmetric vacuum by a potential barrier, meaning that when the transition takes place, the change in the vacuum expectation value is going to be something discontinuous. Okay? This would be a first order transition. Now, currently, the experimental data we have cannot tell among these two possibilities. We only know where the vacuum is and the small perturbations around the vacuum. This is what we measure. Now, depending on the global shape of the potential, we could be in this situation or in this situation. And if we were to be, or if nature would have chosen a first order electric phase transition as a realization, this would be a violent process that would lead to out of equilibrium. So this would allow for electric baryogenesis. Of course, this is only the case experimentally, but if we take a particular theory, we can compute the nature of the electric phase transition in a perturbative manner, and even non-perturbatively. And in the standard model, it turns out, as we heard a couple of slides ago, that the situation perturbatively is more of this sort, and it turns out that non-perturbatively is actually a smooth crossover. So there is no out of equilibrium. However, we also heard it in the introduction, new physics that is sizably coupled to the Higgs can drastically change the electric phase transition nature. And the way it does it is precisely by influencing each of these different parts of the finite temperature effective potential. So for example, if I have multiple fields in my scalar potential, rather than just the Higgs doublet, then I will modify the tree-level potential. I'll have like more fields, more terms, and this could allow for tree-level potential barriers from the multi-field interplay. Also, the new degrees of freedom that couple to the Higgs, they can, so they will give rise to new loop corrections, new thermal corrections, and if these new degrees of freedom are bosons, they can, in particular, yield a potential barrier at finite temperature that is driven by these non-analytic terms in the thermal potential. So all in all, it is possible for BSM to give a first-order electric phase transition towards realizing electric baryogenesis. So what about beyond the standard model CP violation? What about the other ingredient? Now, these non-minimal Higgs sectors that these multi-field setups that would allow for, say, tree-level barriers, or would give as a first-order electric phase transition as one of the possibilities. They, in many cases, can also give new sources of CP violation beyond the standard model. The canonical, the poster child example for this is the two-Higgs doublet model, where I have a theory now with two scalar doublets, and in the case that so these two parameters in the scalar potential, this lambda 5 and this mu1 2 square, so this mass term and this quartic coupling, they can be complex in general, and the relative phase between them, say, so this, the phase of this combination here is actually physical, in the sense that is not redefinable away by phase changes in the scalar doublets. So it's a phase in the scalar potential that I cannot redefine away by changing the phase of the two scalar doublets arbitrarily, and then this means it's physical, it's non-removable from the Lagrangian, and this gives rise to CP violation. So this is good. However, the problem that one faces when dealing with beyond the standard model sources of CP violation, not only these ones in the standard Higgs sectors, but any source normally, is that these new sources are very strongly constrained by experiments, in particular by searches for electric dipole moments. So for example, here you have the current limit from searches of an electric dipole moment of the electron from the ACME collaboration. And if one goes back to the two-Higgs doublet model and sees what the effect of these experimental bounds is, we see that this is extremely strong currently. It's very strong currently and would be even more in the near future. So in the two-Higgs doublet model, the main contribution to the electron EDM comes from these two-loop Barasi diagrams, where in this black blob you have a loop of a particle that is sizably coupled to the Higgs, like a top loop, and it's also charged, of course, in order to couple to the photon. So like a top loop, for example. And in two Higgs doublet models, you see here as a function of tan beta, what is the size of the electric dipole moment. This is in type 2 Higgs doublet model, and this is a recent paper by Almancho, Fergori, Hammer and Patel. And you see here that there are only the black lines is the total contribution to the EDM, okay? The other lines are individual contributions from individual Barsis and other types of diagrams. And you see that only in very tuned regions of tan beta, you get something that is compatible with the EDM bounds. So currently you are here, and in the future you will be here, and it would be even more difficult. You will even have to tune more the value of tan beta in order to escape this. And for type 1 Higgs doublet model, the situation is very similar. Say it's just like different combinations of diagrams. So all in all, one could argue that CP violation is the biggest challenge for successful electric baryogenesis. This is also why one doesn't find so many papers written on this, because it's actually very difficult to address this in a successful manner. And in fact, a few years ago, 3-4 years ago, the fact that this ACME collaboration was putting these new limits, this is from 2018, made many people say that essentially electric baryogenesis was ruled out. I mean, it was very difficult or even impossible to do this in many otherwise very appealing scenarios, where you could do the phase transition, etc. So, sorry. So what I want to tell you about today is the fact that, in principle, a Higgs sector and a minimal Higgs sector could, in fact, help circumvent these electric dipole moment constraints in the following way. So it could induce CP violation in the early universe, such that CP violation would be large or active, say, when baryogenesis would take place around electric scales, and then later on, the very evolution of the scalar sector would suppress CP violation in order to have an approximate CP conserving scalar sector today. And then electric dipole moments would not be sensitive to that, because the EDM would be extremely suppressed. The source of CP violation would be very suppressed now. So this is what we are going to do in the rest of the talk. We're going to try to explore setups in which this works, or how this works, okay? So let me give you an explicit realization, which is based on a two Higgs doublet model plus extended by a real pseudoscalar singlet under the standard model. This is a model that is motivated on its own, not just for this, and we actually didn't build a model for this. We came across this thing that I'm going to tell you while studying the model for other purposes. In particular, is widely used in dark matter literature for dark matter phenomenology at the LHC. And you have the two Higgs model scalar potential with a softly broken Z2 symmetry, okay? And you have also the scalar potential involving the singlet, which would be this part here, and the interactions between the doublets and the singlet. Okay? Now, because I added new terms to the scalar potential, besides the CP violating invariant that I had before in the two Higgs doublet model, which comes from these two terms, I have more reciprocating phases, more reciprocating invariants. So for example, this kappa term here can be complex again, and then I can build another reciprocating invariant by combining this and this, for example. Okay? At the end of the day, there are two independent reciprocating invariants rather than just one. Now, if all the three parameters that I have here are real simultaneously, okay, I have explicit CP conservation in my model. This is a pure pseudoscalar, and I have explicit CP conservation, okay? If the VEF of the pseudoscalar is 0, which this is what I would want at 0 temperature, in order not to break CP at 0 temperature. However, if the VEF was non-zero at any point, this would induce CP violation in my model. So then it is possible to switch on and off this VEF in the early universe in order to get a transient period of CP violation. That's what I'm going to be doing, essentially. There is some subtlety regarding the set to symmetry and CP, how they are connected. I will talk about this later on in the talk. But let me put this under the rug for a second. So this box here fully applies. I switch on and off, and I have transient CP violation. And this is what I'm after. So what the picture is going to be is I start at very high temperatures in a vacuum that is preserving the set to symmetry of the pseudoscalar. In other words, the VEF of the pseudoscalar is going to be 0 at high temperatures. And also the VEF of the Higgses is going to be 0 at high temperatures, so that electric symmetry is also restored. I am going to want to give a VEF to the pseudoscalar singlet at some point in the early universe in order to induce CP violation. And later on, I am going to demand that when electric symmetry is broken, the VEF of the pseudoscalar goes back to 0 in order to restore CP. And then I will have a transient CP violating period. Of course, this sounds amazing, but there is no free lunch. This comes with a handful of requirements in my theory. The first ones are the fact that I need the mass term for my pseudoscalar to be negative in order to be able to induce a VEF for it at any temperature. And then I need that at 0 temperature, the mass of the pseudoscalar is positive in order not to have, in the electrolytic vacuum, in order for the electrolytic vacuum not to be tachyonic. And again, this imposes this condition here. And furthermore, I, of course, need the electrolytic vacuum to be the deepest minimum at 0 temperature in order for my thermal history to make sense and us to arrive where we are today. So those are 0 temperature requirements, and the finite temperature requirement essentially is the fact that I want the desired thermal history that I described in one slide ago. So first, break so give a VEF to the pseudoscalar singlet, and then later on to break the electrolytic symmetry. Now, in order to impose these requirements, in order to follow the thermal history and make sure that this is the way it goes, we wanted to have an analytical control and analytical understanding of what is going on. And one can do this if instead of just writing the entire, say, full one loop finite temperature effective potential with a daisy resummation from higher loop corrections, etc., which is what you would do in a standard precision computational precision study. But there you have to do a full numerical study, and you lose a bit of control of how your parameter space works. Because this is like a proof of principle, or say a proof of concept study. We want to check if whether this can work and where this can work, more or less. What we did was to keep the minimum amount of ingredients we need to make this happen. And the minimum amount of ingredients, having a multi-field potential, we have 3 fields here. We can work with only the 3-level scalar potential plus the leading thermal corrections, which are the thermal masses, say, or the order t² corrections to the scalar potential. So doing this allows you to do a lot of things analytically. You can go a long way with this. And in particular, you can compute the temperatures at which you destabilize each of the field directions. So you can compute the temperature at which the singlet field direction gets destabilized and the singlet gets above. And then you can compute the temperature at which, from the origin, you destabilize the doublet field directions, so you break electric singlet. And then what you have to demand is that you destabilize the singlet first, essentially, in order to first break the break along the singlet direction, and then later on, because you have imposed that the electric minimum would be the deepest at 0 temperature, later on you are guaranteed to have a deeper electric minimum at some point when the temperature drops down sufficiently, and you will go back to the electric vacuum. So this is it. And then when you impose this criteria, first breaking along the singlet direction, then later on going to the electric vacuum, because this one is the deepest at 0 temperature, you get these funnel regions where this transiency violation works. So as a function of other parameters in my model, so there is a mixing angle between the doublet pseudoscalar and the singlet pseudoscalar, and this is the mass of the heavy states from the two-field doublet model, and the singlet wave along the singlet direction. This is the mass of the singlet pseudoscalar, singlet-like pseudoscalar, because it has a little doublet admixture, and this is the coupling between the singlet-like pseudoscalar and the Higgs, and the 125, say. And you see that this in like bottom line, say the line that is the bottom part of the funnel, this comes from imposing that the electric vacuum is the deepest one at 0 temperature, and this upper line comes from the fact of imposing the correct thermal history that you first break along the singlet direction. And then you have these funnel regions. So there is available parameter space. But this is not the only thing you have to do. Now, it turns out that imposing that the universe, so that the electric vacuum is the deepest vacuum at 0 temperature is not enough. You need to guarantee that the universe goes from the singlet vacuum to the electric vacuum at some temperature that is able to transition from one to the other, so that the electric phase transition can take place. And it turns out that this requirement chops off a large region of these funnels, because in this part here, which is hatched, you would get trapped in the singlet vacuum. So the singlet vacuum would be a minimum down to 0 temperature, albeit not the deepest one, but it would be a minimum, and it would be sufficiently stable so as not to allow the transition over the lifetime of the universe. No, sorry. So this is a further requirement, and all in all, there are regions where successful transient evaluation will take place, will happen, but these regions are characterized by a singlet-like pseudoscalar, which is light. Okay? Now, this is regarding the thermal history and the phase transition. So regarding baryogenesis, it turns out one nice thing of this model is that the baryon asymmetry can be straightforwardly connected to the one that you get in the two-Higgs doublet model. So what I mean in practice is the fact that because the source of CPU violation here that is coming from this scalar VEF, as we will see in a second, and the fact that this singlet scalar mixes with the doublet pseudoscalar from the 2HDM, what this is doing at the end of the day is inducing some space-time dependent phase that leaks to the fermions of the standard model via the Yukawas from the two-Higgs doublet model. Now, the size of the CP phase is different in the two-Higgs doublet model and in this model, but the way that the phase, whatever it is, leaks to the fermions is the same as in the two-Higgs doublet model. So then the only thing you need is to compute the phase, which will be different from the 2HDM, but you can plug in that phase in any baryogenesis computation that you do in the two-Higgs doublet model. And since this has been done in many papers, we could just follow that. And in particular, for the two-Higgs doublet model, there was this study from 2007 that computed in a somehow fitted way what is the baryon asymmetry that you would get in terms of thermodynamical quantities in the two-Higgs doublet model. In particular, and in terms of also the size of CPU violation. So, providing that CPU violation is the same as in the it follows the same mechanism as in the 2HDM. So we can use this, just inputting here our CPU violation, and this is essentially what we did. You have here a specific point in the parameter space of the model, what would be the field trajectory from the CPU violating minimum to the electroweak vacuum. And one can compute the size of CPU violation along this trajectory from a simple formula, which is this one, okay, where this mu12 squared T star is just the complex conjugate of this quantity here, and what is evolving as a function of not temperature really, but as a function of this guy here is precisely this VEF. Okay, so now one can compute the baryon asymmetry. Let me take this computation with a grain of salt because it has many uncertainties. We try to capture a bit the effect of these uncertainties by plotting a band of the observed baryon asymmetry. So what we predict would be between half and twice what is observed. Of course, these uncertainties in principle are not confined to this here. So take this plot with a bit of a grain of salt, but the trend is clear, and this would be the same whether the uncertainty would be larger or smaller. So one starts off at very small singlet doublet mixing angle. One starts off with a very light singlet, and then as the mixing angle grows, eventually one reaches a turning point at which one has this boomerang shape effect. And yeah, this is what one gets. And I could explain more or less why this is coming from, but I can leave this for the questions if you're interested. And now regarding the constraints on this parameter space, first below the half of the 125 GeV Higgs mass, this parameter space is ruled out by Higgs signal strengths and by exotic Higgs decays. So we chop off this region here, and then above it, we have two different kinds of searches which are very sensitive to this kind of setup. One are cascade decays of the heavy two-Higgs doublet model guys into the light pseudoscalar plus some other particle, say H0 to ZA1, into leptons plus A1 going to BB bar because A1 mixes with the pseudoscalar doublet, and Atlas and CMS search for this thing, and they put limits which are like fairly strong and will improve quite a lot for high Lumi, as you can see here. These limits go down because this partial width, it scales with the mixing between the scalar, the pseudoscalar doublet and singlet, in such a way that when the mixing becomes very small, this partial width and the corresponding branching fraction goes to zero. However, it is possible to search for this light pseudoscalar also in cascade decays when the mixing angle goes to zero, because we can produce the H0 and it can decay to a pair of these two light pseudoscalars, and unless the mixing angle is exactly zero, it will mix with the pseudoscalar doublet and it will decay back into the standard model. And this search is from a recast of resonant Higgs searches that we did a few years back, 3 years ago, and it turns out that you have sensitivity to this H0 to A1 in a wide region of masses. We don't have there is no current sensitivity below, say, 100-ish GeV, but in the future, with the same search, there will be sensitivity down to maybe 60 or even below GeV. So it would be possible to cover the entire region of parameter space, for example, for this particular point here. And this discussion is general. So if you change the point that you are trying to address, the plot will move a bit around, the bounds will move up and down a bit, but the qualitative picture will be the same. So in principle, this is something that you can probe, at least partially, due to the presence of this light pseudoscalar that cannot be fully decoupled, because so it cannot be a pure singlet, because the mixing angle is what controls, so it's tied to the CP violation, it's tied to baryogenesis. So you cannot go to zero mixing angle, as you see here. Now, let me continue by going back to the subtle tree that I mentioned briefly when I was presenting the model. And this has to do with what one calls local versus global electroic baryogenesis. So what I call local electroic baryogenesis is what one usually has in mind. So in a first-order electroic phase transition, one produces these bubbles of the true phase, of the true vacuum. They expand, and the baryogenesis, the generation of the baryon excess, takes place in the vicinity of these bubble walls locally. So you have these bubbles, and you would zoom here, and you get a net baryon density. Okay, this is the local electroic baryogenesis. Now the global one is, okay, once the process has taken place, you then ask what is the average baryon density per Hubble volume, and this is what is measured. So this is what is observable. So it's you average over a Hubble patch, and this is the net baryon to entropy ratio that you are going to measure with Planck. Okay. Now the thing is, are they the same? In principle, they would be. No, I am at any point in space, I am locally producing the baryon density, and then of course, if I have a local density which is the same everywhere, the global density is the same as the local one. However, in certain cases, like the one for the model I just described, they are not the same for the following reason. So in my theory, I had a single pseudoscalar that took a VEF in the early universe, but I didn't mention it. I mention it now, that it could have, so the VEF could have been positive or negative with equal probability, because the scalar potential along the singlet direction only has a set to symmetry. So there is a term that is odd under the, so it has one singlet pseudoscalar, it's linear in it, but it involves the doublets. So along the singlet direction only, there is a set to symmetry. And this means that in some regions of the universe, I will go to this vacuum. In some regions of the universe, I will go to this vacuum with equal probability, because they have the same energy. But the supervalating phase from this vacuum and from this vacuum will have opposite signs. So at the end of the day, I'll have regions where I have produced a local, say, baryon excess, and regions where I have produced a local anti-baryon excess. And then when I average out, the global baryon density will be 0, up to statistical factors. Okay, up to statistical effects of having a slightly larger region somewhere than others. So one would need an explicit set to breaking along the singlet direction in order to bias one vacuum over the other. And the moment that one has this explicit set to breaking, things will work, because the bias that one needs from one vacuum to the other, the delta, the difference in the scalar potential between the two, needs to be tiny. Any small bias will do the trick. It has to be like delta V over T to the fourth, which is the relevant scale here, has to be much larger than 10 to the minus 16, which is nothing, really. So almost anything will do. However, the set to symmetry and CP are tied together in this model, because this biasing term, this set to breaking term, would also break CP explicitly, because A is a pseudoscalar. And I cannot decide that A is a scalar now, because this will break CP in some other part of the scalar potential. So breaking explicitly the set 2 along the singlet direction would also need CP to be broken. So we need explicit CP violation in order to induce this set to breaking in the scalar potential. Now, if one introduces an explicit CP violation term in the scalar potential, this will radiatively induce this A cube term, and you can do the trick. Despite this being radiatively generated and being small, it is sufficiently big in order to do the bias. But at the end of the day, you need explicit CP violation in your model. So you cannot have a pure spontaneously CP violating model at work. You need some explicit source of CP violation. So we wanted to explore realizations where this would not be a problem. So where we would not have to take care of this biasing of vacua, etc., etc. And say, okay, are there realizations of this transient CP violation period where this problem doesn't exist? And then, of course, I said that you need some explicit CP violation in order for that to happen. And what we did was the following. So this is work in progress. What we are currently doing, say, rather than we did, is the following. Instead of having a term like the one we had before, which is linear in A here, and this is the term that induces the CP breaking at the end of the day, because when A got a VEF, this was inducing the CP violation, we now promote this term to a quadratic term. Instead of having S, we have S squared. We have S squared, S squared. So we have S squared everywhere here. So now there is a set2 symmetry everywhere for the singlet field. Of course, this means that now CP violation will be explicit, because if I want to have a transient CP violating period, I also need, say, if this term is real, this term has to be purely imaginary or complex. And this will induce CP violation immediately, as in an explicit manner. Okay, in other words, before I was having a CP conserving theory by having this thing to be a pseudoscalar, to be CP odd. Now this thing cannot be CP odd because it's S squared. So whatever S CP properties are, this will always be CP even. Now, this has a couple of consequences. This is a hard breaking of the standard model of the two-Higgs doublet model set2 symmetry. So this is a soft breaking of the set2 symmetry, but this is a hard breaking of it, because it's a breaking with a dimension dimension 4 term in the scalar potential. But this is not so bad, because this CP violation and the hard breaking is tied to the dark sector. Okay, so if the singlet was out of the game, there would not be neither hard breaking, neither CP violation. Now, the fact that there is a hard breaking means that there is not a protection in your model against flavor changing neutral currents at all orders, like happens in two-Higgs doublet model of type 1, type 2, etc., even with a softly broken set2 symmetry. So if you have this scalar potential at 3 level, you will induce at one loop scalar terms that only involve the doublets and that also break this set2 symmetry in a hard way, and then at yet another order, you will induce flavor changing neutral currents. So they are suppressed as compared to what you expect in a general two-Higgs doublet model by one order, by one loop, because of this hard breaking being tied to the dark sector. But is a one loop you gain one loop, you don't have like a all order separation. And then the fact that CP violation is tied to the dark sector means that electric dipole moment contributions will need the dark particle to enter into the game, so they will be suppressed again by one order, so from 2 to 3 loops. And this gives enough suppression to uplift a lot the current EDM constraints. Now, these are the good and the bad things in a sense. Another good thing is the fact that because now, since the singlet particle, the singlet spin zero state, enters always as S squared, we have a set2 symmetry in it if it doesn't get a VEF at 0 temperature. And then this dark set2 symmetry for S makes it a potentially viable dark matter candidate. Now, this is good and bad in the sense that dark matter constraints strongly limit the possible parameter space. So it's good, okay, I can solve 2 problems with one model, with one shot, and dark matter would be tied to the very baryogenesis mechanism, to the transient generation of CP violation, because this S would get a VEF during some epoch in the early universe, with not, albeit not having a VEF now. But of course, making it so having dark matter into the game means that you need to be able to satisfy the stringent limits you have on them. And in particular, because I'm going to go back in a sec, because you have dark matter coupled to the Higgses, this is like a Higgs portal dark matter, so scalar dark matter, interacting with the standard model via Higgs portal. Albeit it's a 2 Higgs doublet model portal, because it's not just with S square, H square, is S square with each of the 2 doublets plus this term here. But we know that Higgs portal dark matter faces very strong constraints from direct detection. And you see here, say, the limits on these quantities here from the latest xenon-enton direct detection bounds. Okay? For type 1 2 Higgs doublet model, this RQ is the same for up and down type quarks. And for type 2 2 Higgs doublet model, this RQ is different from, say, between up type and down type quarks. And this can give rise to what's called isospin violating dark matter. So this is work in progress. I have a few more results on this that I didn't have time to put on the talk. It will be out soon enough, we hope, in a couple of months, maybe, something like this. So this is very preliminary. It turns out that these xenon-enton limits, they put very so they impose stringent correlations between the different parameters of your model. So, for example, between tan beta and cos beta minus alpha, for other parameters fixed, you see that there are these strips where you satisfy the direct detection limits. So it is possible to satisfy them, and there are regions of parameter space where you do it in this model, but it's something which is still not surprisingly, because here you are trying to do dark matter baryogenesis, and the limits on dark matter are on top of that strong. Okay, and you can compare this with the latest bounds from Higgs signal strengths on these 2 parameters. So you see that they would chop something like this, more or less. So Higgs signal strengths are able to rule out regions of parameter space that would be acceptable otherwise, because you need some deviation from alignment in type 1 to this doublet model to satisfy dark matter constraints. But there is still room to play. So this goes up to 0.3, which is something like this. Okay, let me summarize what I told you about in this talk. So the main points that I wanted to convey is that beyond standard model CPU evaluation is tightly constrained by EDMs, and this is a threat to electric baryogenesis, a very serious one. But there are ways out of it. And one way out of it, well-motivated one, is that the early units could have undergone a transient period of CPU breaking, and this would essentially circumvent EDM constraints, because at present there would not really be beyond the standard model CPU evaluation, or it would be very suppressed. But in the early universe, it was enhanced enough to allow for baryogenesis. But this needs slight degrees of freedom, which are within LHC reach. So in one realization, this is a light pseudoscalar, 100 GeV or so, or even lighter, that is coupled to the 125 GeV Higgs boson, and that is also coupled to other states that allow for cascade decays. And in other realizations, this could lead to some other light states, for example, even a dark matter candidate. Okay? So thank you very much for this part of the talk. If I have 2-3 more minutes, I want to tell you about some other very quick thing which is related to this, but it explores a slightly different kind of physics. So I will take 1-2 more minutes, and then I will end. So this is a bit of a funky thing. So this is not the extended scalar sector that one is usually used to, say. So what I'm going to be after now, if one takes this idea of breaking symmetries in the early universe and using those symmetry breakings for things seriously, one can like go for funky things, and one of those is trying to break hypercharge in the early universe, and we'll see that this is quite interesting. In fact, this hypercharge breaking in the early universe is very well motivated in certain beyond standard model scenarios, in a particular class of them, which are what are called radiative neutrino mass models. So these are models where neutrinos, standard model neutrinos, they get masses from loop effects, and this explains why their masses are so small compared to other fermions in the standard model, because the masses of these particles get produced at some loop order, which could be 1, 2, or even larger. Now, one working example is the so-called C-Babu model. It's one of the most famous ones. How to do this? You need to introduce new particles to the standard model, and these new particles will be coupled to the leptons of the standard model, and will collectively, those different couplings, will break lepton number. And if you break lepton number, you could generate a Majorana mass for the light neutrinos. But because you need all these couplings to be non-zero at the same time in order to generate that mass, this can only happen at some loop order. So you can only get all these couplings entering into a loop diagram at some loop order. So in the C-Babu, you introduce two new particles, two scalars, which are SU2 singlets, but have non-zero hypercharge, so they are electrically charged at the end of the day. Singly charged, doubly charged. And then they have coupling to leptons. So, for example, the doubly charged couples to the right-handed charged leptons in a Majorana way. So you have a Majorana mass for the right-handed charged lepton, which is gauge invariant SU2, SU3, Lorentz invariant, is just not hypercharge invariant. So if you put then a scalar which has hypercharge, you gauge invariantize that term, and you have a Majorana term for the right-handed charge lepton. And similarly here, okay? And in this model, you get a neutrino mass at two loops. So it's quite small. Now, it turns out that in these models, you have multiple scalars, have the Higgs and two others. Some of them have non-zero hypercharge, and they couple to the leptons. So the thermal corrections in these theories could induce an early universe VEF for one of these guys. And if they do, you will break hypercharge in the early universe. This is as simple as this. So then one can study what are the regions of parameter space in the C-Babu, for example, where this happens, where you induce an early universe VEF for any of these two, essentially. And this implies studying the effective mass for these fields at high temperature. So again, the T-square corrections. So computing the leading order thermal correction for to their bare mass, and see what is the sign of this coefficient here. Now, it turns out that this is a technicality. It's important to keep at that T-square order not only the one loop leading order T-square, but also multi-loop configurations, the Daisy terms, which also induce order T-square part, and they shift these coefficients, and one needs to take this into account if you are working at high temperature. And then when one does this, we just did a Monte Carlo scan of the different quartic couplings of the scalar potential with the three fields, and there is a region where one does find some of these coefficients, either C rho or C kappa, or both of them, are negative, meaning that in the early universe you will break hypercharge. And then this can actually allow for baryogenesis, because you will have an early universe where you have broken hypercharge, and you have a BEF for one of these fields, and you will end up wanting to transition to a universe where these guys don't have a BEF, and the electric symmetry is broken. And then if there is a potential barrier between these two vacua in the early universe, you have a first order phase transition. And at the same time, because you have a BEF for you have a hypercharge breaking vacuum that you are coming from, say, and in the phase transition, you are evolving from it to the electroic one. These terms here, the ones that couple the charge fields to the fermions, they will act essentially as effective masses for the leptons when these fields get a BEF. And then you will have an effective mass that is changing across the phase transition that can have complex phases on it, because this mass matrix, or well, this Yukawa matrix have complex phases. And these Yukawa matrices, the couplings are not very small, because these couplings enter into the neutrino masses, but the neutrino masses are very suppressed by the loops. So these Yukawas are, I don't know, maybe 10 to the minus 1, 10 to the minus 2, something like this. So you end up having something which is similar to what you would have in a normal electric baryogenesis setup, rather than with the quarks, say with the top or the bottom, with these leptons. So these are the usual charge leptons. Okay? But their Yukawas with these guys are large. They are not very small. So you could, and they are potentially superlative. So you could do baryogenesis in this way. Okay, this is the end of my bonus. Thank you very much. And sorry for the slight go over time.
Okay, thank you for the nice talk. So if we have time for questions from the audience, please.
Yeah, hi, Jose. So it's
Hi.
Yongchen here. Yeah, so I'm wondering, like you mentioned the constraint from the LHC alpha CMS for the first case. I think it's the for the singlet, and so you show the future coverage from the H0 to singlet will cover most of this product cover most of space. And does those search depends on the mass of this H naught? And,
yeah. Totally. Yeah. So both searches, so the one in green and the one in orange, they depend significantly on the mass of the H naught. One important clarification. So the orange search does not exist yet. So this is I think I said it quickly. So the search that does exist is a CMS search, which was looking for H naught to 125. So it's a resonant Higgs search. We then, so that search, which this was from 2018, that search gave enough information to recast it for other masses beyond 125 for the daughter particles. So you could say, I have a general search which have H naught to some pair of equal mass guys, with a mass different from 125 in principle, and we basically derived the would-be limits that such a search would put given the data that CMS was giving. But it's a recast rather than rather than a true search. So these are
Mhm.
this is like showcasing the potential of the search that they did to constrain other regions of parameter space rather than actually like actual limits. We think that if one would do this thing and one would not find anything, the limits would be like very much there because the recast was agreeing very well with what you get for resonant Higgs when the mass of these guys is 125 GeV. So it looked like this was kind of properly done, but the search doesn't fully exist.
Okay.
So just as a like a heads up. And then the other thing that you said, this in this plane here, we have to fix the H naught mass to 400 GeV, but of course, green and orange will change significantly if you decrease or increase this. If you increase this to, I don't know, like in our paper, we had another plot with 850, I think, or I don't know if we put it at the end, but we in the beginning, we had another plot with M equals 850. And you could see that, of course, the searches lose stamina. I mean, they keep on constraining regions of parameter space, but they don't like fully cover everything. Say, the good thing is that in principle you cannot fully decouple this guy here, or I mean, you can partially decouple it, but like I'm not sure that you can take this. This H naught to be, I don't know, like 2 TeV and still have a mixing angle which is sizable.
Yeah, and also like if we have much heavier scalars here, the strength of the electric phase transition will be weaker, right?
Yes, exactly. Also, yeah.
Yeah. Okay.
So somehow it
yeah.
tells you that you cannot go very much above like I don't know, like 700-800 GeV. So actually, I recall now that in the 2HDM, so without the extra singlet, but the conclusions with the extra singlet would be exactly the same. You had on your paper with Dorival that, as you just said, you could not go to masses very heavy and have a strong first order phase transition. So if you want that, you still need like light guys. From the phase transition point of view, this would change a bit in here because the transition is driven also by the going from the singlet to the doublet, but still I would definitely expect that this is still the case. You cannot decouple them.
Yeah. Okay. And the another question is, when we introduced a small explicit Z2 breaking term to have the global electroweak baryogenesis here, so will we have much? Should we have much larger CP violation to generate enough like baryon asymmetry? Then what's left from the two equivalent vacuum will be the final observed baryon asymmetry.
Can you repeat the question? Sorry.
Yes. So in this case, you introduce a explicitly Z2 breaking term. So, and these two equivalent Z2 related vacuum, they will generate opposite sign by symmetry, and what's left is what we observed right now. So should we need to have much larger CP violation to generate much larger?
No. Sorry. This I didn't explain well. So once I say I introduce a tiny amount of explicit CP violation, tiny, say, in a phase that is 10 to the minus 4. So something that would be unobservable in EDMs today. That phase of 10 to the minus 4, which enters as an imaginary part in this cross here, then via the loop diagram, it also generates this A cube guy. And this A cube guy is the 10 to the minus 4 phase times some ratio of scales, whatever, times a loop factor. So it's, I don't know, 10 to the minus 7, something like this. This ends up giving, so probably the 10 to the minus 7 is going to be pretty small. I wanted something which is slightly larger, but anyway. So I end up with something which is, which gives me a delta V, which is delta V over T to the 4, which is 10 to the minus 12 or something like this. I'm just throwing numbers, but like a small amount of circulation that ends up giving me something which is a small bias, so something which is 10 to the minus 12 in T to the 4 units, but so say unobservable in EDMs, but is still much larger than this 10 to the minus 16. If it is larger than 10 to the minus 16, albeit unobservable experimentally, this means that I will have regions with positive guys. I will have regions with with positive VEF. I will have regions with negative VEF. But because of this tiny bias, by the time that I want to tunnel to the electrolytic VEF, so by the time that I want to produce these bubbles and generate the local baryon density, the deepest of the two will have eaten the other one. So there will only be one phase. So this
at the
this
end,
is
only one phase exists during this, during the first step. Okay.
So during the first step, I produce the two, but in the time from the first step to the second step, the deepest phase eats the other one. So then by the time of the second step, there is only one phase, the deepest of the two.
Oh, so at the second step, only the one has deeper potential wins and generates bias.
Yes.
Okay,
So all the universe is on the deepest potential, and then locally you only have bubbles with, say, positive phase or bubbles with negative phase, the one which was deepest.
Yeah, so it first eat the other one, then generate the bias enrichment, not simultaneously generate bias enrichment, and they give the remnant bias.
No. So you first roll to the two of them, but one is higher than the other, and then because of this small potential difference, it is more favorable for one of the two domain regions to grow over the other, and over a short time scale in Hubble units, the one eats the other. So this is described in this paper here. This has to do also with domain wall physics and the like. So it's not something that is like specific of this model.
Yeah. Okay. Thank you.
That way, you are done. So then the amount of simulation you need is quite small. So we didn't actually compute, and this is something we would probably want to do in the future, how small this needed to be. But you have all the ingredients in principle. You have, okay, so this is what I need. I know what so we gave a formula for mu3 in terms of of these quantities here. So one could very quickly estimate what is the size of the superality of the split superality phase that one needs to get something which is larger than 10 to the minus 16. So say one order of magnitude larger would suffice. This phase is very small. It's unobservable in EDMs, although it's different from zero.
Okay, good. Okay. Thank you.
So we have a question from Peter.
Yeah, sure. So I'm just wondering about the models. So in all cases, it's kind of constructed in order to solve the problem, but do you have some deeper idea of where these can come from?
Yeah. Thanks for the question, actually. So I mentioned it a bit in passant, but I didn't go at all onto it. I don't know if I have a slide on that in the backup. Let me see. So for realization one, so the second realization was constructed explicitly to solve both the transiency evaluating problem and also the same as the realization one is doing, but also the fact that this realization one was having this set two problem that I just described. But the first setup we worked with, this model comes from a different place. So let me see if I have it in the backup slides. Yes. So it turns out that this two-Higgs doublet model plus singlet pseudoscalar has been very widely used in the dark matter community if as say a pseudoscalar portal to dark matter. And so forget for the time being about the two doublets and so about this part of the potential and all this really. So just consider the pure singlet part here and this part here. Okay, so the reason why people have been studying a pseudoscalar portal to dark matter in the past few years is, say, you have a singlet fermion dark matter, and then you want to connect it to the standard model via some kind of interaction. And there were some simplified models that were devised for this, like via a vector, an axial vector, a scalar, or a pseudoscalar. Now, it turned out, and this was very widely used in searches at the LHC for interpretations, and also for interpretations of direct detection, indirect detection, etc. Now, it turns out that like more than 10 years ago, there was a possible signal of dark matter coming from dark matter annihilation in the galactic center. So this was called the galactic center excess. And this was impossible to reconcile with direct detection limits if the mediator were a scalar or vector. Because in a scalar or a vector mediator case, in particular for a scalar one, which is the one I'm more familiar with, it turns out that the dark matter direct detection cross-section is spin independent, and the limits are super strong from xenon and so on. At the time from LAX, etc. So then the only way that was devised to reconcile this possible dark matter signal with the limits from direct detection was to get rid of the direct detection limits somehow. And you could do this if the mediator between dark matter and the visible sector was not giving rise to spin independent independent cross-section, but rather to a spin-dependent one. And a pseudoscalar would do that for you, for example. So then, so this was like kind of the poster child for this. Say like, I have a pseudoscalar mediator between dark matter and the visible sector. This, for relic density, for indirect detection, works just fine, but there is no direct detection signal at tree level because it doesn't give rise to a spin-independent cross-section because of its pseudoscalar nature. So this became very popular, and there are like a plethora of papers that analyze this in this pseudoscalar setup. But it turned out also that the model per se, if you write it this way and this way only, because dark matter is a singlet and the pseudoscalar has to be a singlet also in order for this to be gauge invariant, you cannot couple it directly to the standard model. You need to do something. So you need to gauge invariantize your theory, because people were using simplified models that were not gauge invariant. It was just like a phenomenological description, say. And what some people realize, so the first paper is from Ann Nelson, Seda Ipek, and David McKean, and then like a handful of papers ensued, including one with me and Dorival, and also some other people, Martin Bauer, Uli Heitz, etc. Is that the simplest way of make this model gauge invariant was to promote the Higgs plus pseudoscalar singlet to a two-Higgs doublet model plus pseudoscalar singlet. In that way, you could have a theory that was gauge invariant, where you would have this pseudoscalar singlet connected to dark matter, but the way that the pseudoscalar singlet would be able to talk to the two-Higgs doublet, so sorry, to the visible sector, to the actually to the fermions of the standard model, was by mixing with a part of the doublet. And the model that is put forward in this paper, for example, and this is a paper that was trying to address the galactic center excess with a normalizable model and so on and so forth, is precisely this one, is this very model. Essentially, I think these last two terms here, the a square h1 square a square h2 square, they were just not there simply because they didn't need them, but they are there by gauge invariance. So the model itself was used for dark matter like long ago, and then I think it was Ken Nimasu realized one day, like in I don't know, like 3 years ago, more or less, that by playing with this thermal history business, this model could precisely realize a VEF for the pseudoscalar in the early universe. And the idea was to try to get a 3-level barrier rather than to do the transient evaluation and the like. Was try to get a model that could have a 3-level barrier and have a stronger phase transition than usually than you usually have. But then, if you take the entire model by having the 3-level barrier and like having these 2 steps, you also get the transient evaluation. And we came across that like by chance in a sense. But for the model comes from here. And what we are actually doing now is because we didn't do it in the previous paper, we didn't put the dark matter into the game. This coupling here was absent. What we want to do now is, okay, repeat the analysis, having this guy also into the game, trying to connect this also to dark matter.
So
the second implementation, but in this pseudoscalar business.
Okay, so I see. So in a sense, this is already more complete than what people were originally doing in dark matter. But this model, by the way, I remember now also. I think it's exactly this model can also explain mu on G-2. So there's a paper by Juadi and somebody else, I forget who. Which is the G-2.
There are a handful of papers. So this Juadi, Giorgio Arcadi, and some other people on this for direct detection and also like low energy physics. And I think they could. This is the mu G-2 that you are referring to. Yeah,
that's it. Yeah, so
thanks.
Yeah, okay. Yeah, so that's interesting. I still wonder though if this could be built into something bigger still, because it's still a bit ad hoc to just have 2 big stuff.
Very ad hoc. It's like yeah. It's it would be interesting to see if rather than a bottom-up approach, one can try to do a more like top-down approach. Say like, okay, this is coming from a higher theory, say, because this has the like hierarchy problem and all that jazz. I mean, it can solve it can solve dark matter, baryon asymmetry and the like. So it can solve quite a bit of like a handful of problems, but it's always bottom up. So you are not caring about what is the real UV thing that you have there. Okay. Plus, I'm not entirely sure. This is also one thing that would be worth, I would want to check at some point. What is the validity of the model at high scales? Because if you have some like sizable quartic, then you might not like trust this model up to arbitrarily high scales. So I don't know.
So let me ask one last very quick question because it's almost past. But you with this model, you were going to you talked about the treatment of the effective potential, and I think you were saying you just use the approximate treatment, right? For analytical purposes. But are you going to check it numerically in future, or?
Yes. So for when we add this guy into the game, so the dark matter and so on, we'll also profit to try to do like not more than, but at least full one loop Coleman-Weinberg thermal potential one loop with TACEs. So the usual thing that is okay, this is like more or less established. Yeah, we will try to we will do that analysis.
You're planning to do it that way rather than with 3D EFT because it's just because it's more standard in the literature, or because you already have it's easier to implement?
Because neither of us are experts on the other thing at all. So, but we could try to consider also trying to do that maybe at a second step. Afterwards. Yeah. So we are doing this with Stefan Huber, who has a PhD student that is like learning on the way. And so far, what Stefan has like put him to do is more like the canonical perturbative thermal effective potential. But it could be interesting to also have him work on that direction. Yeah.
Okay, good.
Thanks
good
for because yeah, that I mean, given that he's also starting he's like 1 year into his PhD or something like this. That could also maybe be interesting for him.
Okay, thanks a lot.
Thank you.
So if we don't have another question, so we can let's thank again to me and Jose. Thank you very much for the nice talk and the answers.
Thanks a lot. And yeah, it was a pleasure. And say greetings everyone. I mean, it's a pity that I have to do this online, but hope to see some of you soon at some point.
Okay. Yeah. I hope so.
Yeah, by the way, could you send us your slides and we will post it on our website?
Granted.
Okay, good. Thank you.
Thank you.